So, in the last section, we talked about drawing graphs of different functions that had different equations. And in this section, we're going to talk about functions in the real world. So, basically, there are often situations in the real world that um, are basically two variable quantities that are related in such a way. Um, or, in other words, that one variable will depend on the other variable. For example, the position of a speedometer needle depends on how fast the car is going, or the distance you travel depends on how long you've been traveling. The weight of a person depends on his or her height, and so on. So, in cases like these, there is a function of that one variable depends on the other variable. And if you know something about the relationship between the two, you can write an equation relating them and even draw the graph. And in this section, we're not going to be writing any equations between two variables, but we are going to be sketching a reasonable graph. So for this first example, we're given the information that the time it takes you to get home from the football game and the speed that you drive are related to each other. So we're going to sketch a reasonable graph showing this relationship. And so first, we're not told which variable depends on the others, so we first have to figure that out. So the two variables that we're given, the first variable we're gonna either name x or y is going to be the time uh, spent driving home, and the second variable is the speed. So there are two statements we could write. The time traveling home depends on the speed that you drive, or the speed that you drive depends on the time that it took to get home. Now, the second statement really doesn't make much sense. And what makes more sense is that the time taken home depends on the speed that you go. So in that case, speed would be the independent variable. So we're going to call that x. And the time spent going home depends on the speeds. That's the dependent variable, so we'll call that y. So now that we've figured out which one is the independent and dependent variable, we have to draw the graph. So let's first start by setting up our axes. So we're going to call this speed and this time. So we can now figure out both the domain and range too. Since we're dealing with speed, which is an absolute value, we know that the speed is not going to be negative. So we can say that the speed is such that, or the domain is such that x has to be greater than or equal to 0. In the range, we know that we're not going to be dealing with any negative time because you're not going to be getting home before you start. So the range can also be such that y is greater than or equal to 0. Um, and so now what we need to do is plot a couple points. So to figure out what the graph looks like, we need to first pick some moderate speed and then think about what the length of time would be to get home. So let's say we picked some speed around here, and at this speed we're going to say it takes I don't know, about this many seconds to get home. So we're just going to plot a point right there. Now, if we start going faster, it's going to take less time to get home. So time is going to be getting closer to 0 as speed gets more positive. Whereas if your speed was less than this moderate speed, it's going to be taking more time to get home. So this will the time will be greater. So then at this point, we can see the relationship. It's going to be a smooth curve. So we can draw a smooth curve connecting these points. But we know that even as your speed gets faster and faster and faster, it's always going to take some amount of time to get home. So it's never going to reach the x-axis. It's never going to reach 0 there. So we call that an asymptote. and that is denoted by just the one arrow pointing towards. So an asymptote is a line in which the graph gets arbitrarily close to, but never touches, as the dependent or as the independent or dependent variable gets very large, in the positive or negative direction. So what that means is, as let's say the dependent variable is getting very large in the positive direction, this graph is going to be approaching this dotted line, which is called the asymptote, but it's never going to actually touch. So it'll be getting infinitely and infinitely closer, but never touch. And there's also an asymptote in the vertical direction. So as the y variable the dependent variable gets larger in both the positive and negative direction, both these graphs are going to be approaching this dotted line, which is the asymptote. So in this example, you take a roast beef from the refrigerator and put it into a hot oven. The temperature of the beef depends on how long it has been in the oven. Sketch a reasonable graph. So we're already given or explicitly told which variable would be the independent and which variable would be the dependent variable. So the independent variable, which we'll call x, would be the time it has been in the oven, or time since it was taken out of the refrigerator. While the dependent variable y would be the temperature of the roast beef. So now we probably want to figure out the domain range of this. So we're going to say for the domain that time 0 is when the roast beef was put into the oven. So for that, in that case, the domain would include both positive and negative values of time, because the time before it was put in the oven, when it's in the refrigerator, would be a negative value. So we're going to say that the domain would be all real numbers. And that's not the best all reals, but that's okay. The range, on the other hand, would be basically the temperature from when it is in the refrigerator to when it reaches its maximum temperature in the oven. So it's not really all reals, but we're gonna probably say it's both positive values. But really, we can say just the range is from when the temperature in the refrigerator to the temperature in the oven. So at this point, we can now draw the graph. So we know there's both going to be positive and negative values of time, so we want to show that in our axes. So we'll draw the graph in like this. We're going to label our axes now and call this time, and this temperature. And then at time equals 0, we're gonna say that it entered the refrigerator, or it was taken out of the refrigerator and put in the oven. So we're gonna say put in oven right here. So prior to this, the roast beef is staying at a constant temperature, whatever the temperature is in the refrigerator. So we're gonna just stay right here, but it's gonna be a constant line. It's not gonna be changing from when. So we'll label this and just call that fridge temp. And at this point, the roast beef is going to be gradually increasing until it reaches the maximum oven temperature. So we're going to say that this is the max oven temperature. Now, the actual roast beef will probably never actually reach that temperature, and it definitely won't go past that temperature. So we can tell that this is already going to be an asymptote. So the temperature is going to be increasing first more rapidly and then slowly level out until it reaches close to that maximum oven temperature, though it actually will never reach. So we're going to call this an asymptote. So for this section's example problems, um, the a good strategy for these problems is to always start by figuring out which variable is going to be the independent variable and which one is going to be the dependent variable. So figure out independent and dependent. At that point, you're going to want to figure out which variable, you're going to want to figure out the domain range of these variables, because that will help you draw the reasonable graph. And step 3 is just going to be to sketch the graph. So you're going to want to analyze the situation, think about what could happen in this situation, and just sketch the graph accordingly.